In poker, the probability of many events can be determined by direct calculation. This article discusses computing probabilities for many commonly occurring events in the game of Texas Hold'em and provides some probabilities and odds for specific situations. In most cases, the probabilities and odds are approximations due to rounding. When calculating probabilities for a card game such as Texas Hold'em, there are two basic approaches. The first approach is to determine the number of outcomes that satisfy the condition being evaluated and divide this by the total number of possible outcomes. For example, there are 6 outcomes for being dealt a pair of aces in Hold'em, or unregistered trademark yen, or unregistered trademark or unregistered trademark, or unregistered trademark or unregistered trademark pound, or unregistered trademark yen or unregistered trademark, or unregistered trademark yen or unregistered trademark pound and or unregistered trademark or unregistered trademark pound. There are 52 ways to pick the first card and 51 ways to pick the second card and 2 ways to order the 2 cards yielding possible outcomes when being dealt 2 cards. This gives a probability of being dealt 2 aces of. The second approach is to use conditional probabilities, or in more complex situations, a decision tree. There are 4 ways to be dealt an ace out of 52 choices for the first card, resulting in a probability of. There are 3 ways of getting dealt an ace out of 51 choices on the second card after being dealt an ace on the first card. For a probability of this value is the conditional probability that second card dealt is an ace given the condition that the first card dealt is an ace. The joint probability of being dealt 2 aces is the product of the 2 probabilities. This article uses both of these approaches. The odds presented in this article use the notation x1, which translates to x to 1 odds against the event happening. The odds are calculated from the probability p of the event happening using the formula, odds equals 1 AP, 1, or odds equals 1 AP, A1, 1. Another way of expressing the odds x1 is to state that there is a 1 in x plus 1 chance of the event occurring, or the probability of the event occurring is 1/x plus 1. So for example, the odds of a roll of a fair 6-sided dice coming up 3 is 5-1 against, because there are 5 chances for a number other than 3 and 1 chance for a 3. Alternatively, this could be described as a 1 in 6 chance or probability of a 3 being rolled, because the 3 is one of 6 equally likely possible outcomes. Starting hands equals single hand equals. The probability of being dealt various starting hands can be explicitly calculated. In Texas Hold'em, a player is dealt 2 down cards. The first card can be any one of 52 playing cards in the deck, and the second card can be any one of the 51 remaining cards. This gives 52 a, 51 a 2 equals 1,326 possible starting hand combinations. Since the order in which you receive the first 2 cards is not significant, the 2,652 permutations are divided by the 2 ways of ordering 2 cards. Alternatively, the number of possible starting hands is represented as the binomial coefficient, which is the number of possible combinations of choosing 2 cards from a deck of 52 playing cards. The 1,326 starting hands can be reduced for purposes of determining the probability of starting hands for Hold'em or Euro. Since suits have no relative value in poker, many of these hands are identical in value before the flop. The only factors determining the strength of a starting hand are the ranks of the cards and whether the cards share the same suit. Of the 1,326 combinations, there are 169 distinct starting hands grouped into 3 shapes, 13 pocket pairs, 13 a, 12 a 2 equals 78 suited hands and 78 unsuited hands. 13 plus 78 equals 169. The relative probability of being dealt a hand of each given shape is different. The following shows the probabilities and odds of being dealt each type of starting hand. Here are the probabilities and odds of being dealt various other types of starting hands. Equals starting hands heads up equals, for any given starting hand, there are 50 a, 49 a 2 equals 1,225 hands that an opponent can have before the flop. Therefore, there are possible head-to-head matchups in Hold'em. However, Since there are only 169 distinct starting hands, there are 169 or 1,225 equals 207,025 distinct head-to-head matchups. It is useful to know how two starting hands compete against each other heads-up before the flop. In other words, we assume that neither hand will fold, and we will see a showdown. This situation occurs quite often in no-limit and tournament play. Also, studying these odds helps to demonstrate the concept of hand domination, which is important in all community card games. This problem is considerably more complicated than determining the frequency of dealt hands. To see why, note that given both hands, there are 48 remaining unseen cards. Out of these 48 cards, we can choose any 5 to make a board. Thus, there are possible boards that may fall. In addition to determining the precise number of boards that give a win to each player, we also must take into account boards which split the pot, and split the number of these boards between the players. The problem is trivial for computers to solve by brute force search. There are many software programs available that will compute the odds in seconds. A somewhat less trivial exercise is an exhaustive analysis of all of the head-to-head matchups in Texas Hold'em, which requires evaluating each possible board for each distinct head-to-head matchup, or 1,712,304, 207,025 equals 354,489,735,600 results. Head-to-head starting hand matchups. When comparing two starting hands, the head-to-head probability describes the likelihood of one hand beating the other after all of the cards have come out. Head-to-head probabilities vary slightly for each particular distinct starting hand matchup, but the approximate average probabilities, as given by Dan Harrington in Harrington on Hold'em, p. 125, are summarized in the following table. These odds are general approximations only derived from averaging all of the hand matchups in each category. The actual head-to-head probabilities for any two starting hands vary depending on a number of factors, including suited or unsuited starting hands, shared suits between starting hands, connectedness of non-pair starting hands, proximity of card ranks between the starting hands, proximity of card ranks toward A or 2, possibility of split pot. For example, or unregistered trademark pound versus car unregistered trademark QA unregistered trademark pound is 87.65% to win, but or unregistered trademark pound versus 7 unregistered trademark 6 unregistered trademark is 76.81% to win. The mathematics for computing all of the possible matchups is simple. However, the computation is tedious to carry out by hand. A computer program can perform a brute force evaluation of the 1,712,304 possible boards for any given pair of starting hands in seconds. Equal starting hands against multiple opponents equals, when facing two opponents, for any given starting hand the number of possible combinations of hands the opponents can have is hands. For calculating probabilities we can ignore the distinction between the two opponents holding or unregistered trademark jar unregistered trademark yen and 8 unregistered trademark 8 yen and unregistered trademark pound and the opponents holding 8 unregistered trademark 8 yen and unregistered trademark pound and unregistered trademark jar unregistered trademark yen. The number of ways that hands can be distributed between opponents is. So the number of unique hand combinations against two opponents is. And against three opponents is. And against opponents is, or alternatively, where is the number of ways to distribute cards between hands of two cards each? Is the double factorial operator. Is not. The following table shows the number of hand combinations for up to 9 opponents. An exhaustive analysis of all of the matchups in Texas Hold'em of a player against 9 opponents requires evaluating each possible board for each distinct starting hand against each possible combination of hands held by 9 opponents, which is. If you were able to evaluate 1 trillion combinations every second, it would take over 670 million years to evaluate all of the hand board combinations. While it is possible to significantly reduce the total number of combinations by pruning combinations with identical properties, the total number of situations is still well beyond the number that can be evaluated by brute force. For this reason, most software programs compute probabilities and expected values for hold'em poker hands against multiple opponents by simulating the play of thousands or even millions of hands to determine statistical probabilities. Dominated hands equals. When evaluating a hand before the flop, it is useful to have some idea of how likely the hand is dominated. A dominated hand is a hand that is beaten by another hand and is unlikely to win against it. Often the dominated hand is only a single card rank that can improve the dominated hand to beat the dominant hand. For example, KJ is dominated by KQA. Both hands share the king, and the queen kicker is beating the jack kicker. Barring a straight or flush, the KJ will need a jack on the board to improve against the KQ. A pocket pair is dominated by a pocket pair of higher rank. Pocket pairs, barring a straight or flush, a pocket pair needs to make 3 of a kind to beat a higher pocket pair. See the section after the flop for the odds of a pocket pair improving to 3 of a kind. To calculate the probability that another player has a higher pocket pair, first consider the case against a single opponent. The probability that a single opponent has a higher pair can be stated as the probability that the first card dealt to the opponent is a higher rank than the pocket pair and the second card is the same rank as the first. Where is the rank of the pocket pair? There are 4 cards of higher rank. Subtracting the 2 cards for the pocket pair leaves 50 cards in the deck. After the first card is dealt to the player, there are 49 cards left, 3 of which are the same rank as the first. So the probability of a single opponent being dealt a higher pocket pair is. The following approach extends this equation to calculate the probability that one or more other players has a higher pocket pair. Multiply the base probability for a single player for a given rank of pocket pairs by the number of opponents in the hand. Subtract the adjusted probability that more than one opponent has a higher pocket pair. Where is the number of other players still in the hand and is the adjusted probability that multiple opponents have higher pocket pairs, then the probability that at least one of them has a higher pocket pair is. The calculation for depends on the rank of the player's pocket pair, but can be generalized as: where is the probability that exactly 2 players have a higher pair, is the probability that exactly 3 players have a higher pair, etc. As a practical matter, even with pocket 2s against 9 opponents, and so just calculating and gives an adequately precise result. The following table shows the probability that before the flop another player has a larger pocket pair when there are 1 to 9 other players in the hand. The following table gives the probability that a hand is facing 2 or more larger pairs before the flop. From the previous equations, the probability is computed as. From a practical perspective, however, the odds of outdrawing a single pocket pair or multiple pocket pairs are not much different. In both cases, the large majority of winning hands require one of the remaining 2 cards needed to make 3 of a kind. The real difference against multiple overpairs becomes the increased probability that one of the overpairs will also make 3 of a kind. Hands with 1 ace, when holding a single ace, it is useful to know how likely it is that another player has a better an ace with a higher second card, since a weaker ace is dominated by a better ace. The probability that a single opponent has a better ace is the probability that he has either AA or X, where X is a rank other than ace that is higher than the player's second card. When holding X, the probability that a chosen single player has AA is. In the case of a table with opponents, the probability of one of them holding AA is. If the player is holding X against 9 opponents, there is a probability of approximately 0.0218 that one opponent has AA. Where is the rank to a K of the second card? The probability that a single opponent has a better ace is calculated by the formula. The probability of a player having I, where Y is a rank such that X,